Okay, I think we can start because it's already 12:08. So I'll just share my screen. You should be able to see my screen.
Yes, perfectly.
All right, so let's start. So how are you guys? Did you have time to go through the lectures? Anything you want to say? Any suggestion? Anything? If anyone want to lead or want to talk in like any section, go ahead. Ideally, it would be like perfect if this is more interactive. So for today, like the goal is to go through lecture 5 and 6 in the first half an hour, and then we'll jump to a paper. Like I suggested 2 papers, line and PPR Go. But I took line since I know that paper, so I don't have to read that paper. And also we'll go through the 2 collabs and maybe discuss if we work in the handouts. So let's start. And if anyone wants to say something, feel free just to interrupt me like at any point. So I'll start. Like last week, we saw another embeddings on PageRank. The lecture of this week is more about like message passing and not classification, and also an introduction to GNNs. So I'll try to go quickly because I assume most of you guys went through the lectures. So let's start. So the goal here is like, we saw that we can embed graphs and the common tags that the extracting hand features from graphs, but now also like we want to do not classification. So how do we do this? The setting of this problem is basically we have a graph and some of the nodes, those are unlabeled. So we want to predict the labels of those nodes. And the main intuition here is basically that we want to take advantage of the graph. So how the graph is connected, we want to take advantage of all these correlations, and basically then try to predict if a node belongs to a class or not. So we have like 3 ways of doing this, like a relational classification, iterative classification, and relief propagation. So first of all, it's like, okay, but we have those techniques, but how do we know that this correlation exists? So the main assumption is like the nodes that are close to each other, those nodes carry like some meaning. So in a social network, my friends, I should have like a link between my closest friends and friends that are not that close. Maybe there is a hub, but the friends of my friends, also there might be some connection. So that's basically the main assumption of the correlation. So basically they start like with 2 types. So you have homophily, which basically we use that in most classification tasks, where you have the characteristics of a graph and we want to go to a social network. So in that sense is if we have like people, so that will be like a characteristic of each node, how these people are connected. So that will be the social aspect. But the other way, it would be like if we have a social connection, we want to predict many of these characteristics. So we could say like, I have movies, so I want to see if a user likes a movie X to Y. So how do we predict this characteristic, like liking? Sorry. So that would be more the influence. It's just the other way. So it's just how to want to frame it. So that's how we decide like this correlation. That's the main intuition of why how we can define the similarity. We saw in other embeddings that most of it we have a framework, which is encoder decoder. And this depends on 2 things. How do we embed nodes and this similarity function? So this part of like, if we find like neighbors and how correlated is this graph, is called like Gilbert association. So if I am connected to a node with a label X, then I'm likely to have label X as well to my neighbor. And the goal also is like to take advantage of different features for nodes, not only use the graph structure, but also like if I have some other knowledge or other features that can help to that task, we want to take advantage of that. So here we are in a semi-supervised setting where we know some nodes and some other nodes we don't know. So we want to predict the unknown labels. And so as always, we have the agency metrics to different classes, and this can be applied to different applications. So now, how do we do this? Like in general, we have the setting. So okay, we went to the node classification, and we want to take advantage of this influence of the network. So we have three ways of doing this, like a local classifier, a relational classifier, and collective inference. So we'll go through each one of these next. But the basic setting here is that given a neighborhood, I want to predict if the next, given the neighborhood of a node, of a subset of the graph, I want to predict if the current node belongs to label Y. So that will be this Markov assumption. So that's all of them. All of the techniques are based in this one. So far, so good. Everyone on track. Yeah, take that as a yes. So then we'll go like with relational classification, which is the easiest one. Okay, and here again, like the main motivation is like similar nodes are typically close to each other, or we can assume that they are directly connected. So in a relational classification, it's just basically just a classifier. Where we want to is flat, and we don't use the node attributes. We just basically do a classifier where we pass a node v, and we want to predict the class probability if that node belongs to that label or not. And for the nodes that are unknown, we basically initialize them as with the probability of 0.5, which is unknown. Okay, so the idea is like to update the probability in an iterative way until this converges. So this will be like the equation. So I have my agency metrics, I have an edge, how those are connected, and I want to predict basically by averaging the neighbors. So if I know if a node is closest to, so it will be the overlap of the neighborhood. So even if a node is close to a higher quantity of neighbors, it will be most likely that that node belongs to that neighborhood. So that's basically like relational classifier. And this one has a problem that we don't use node feature information, and convergence is not guaranteed. So I won't go through the example, I just skip this. But if you guys have any questions, just feel free to ask. All right. So the second way is like iterative classifier, because the previous one we saw that basically doesn't use like node attributes. So we want to take advantage of these attributes. So in the iterative classifier, now we have two classifiers. One that basically it takes the feature, the vector information, so the node attributes, and we try to write a class to build a classifier around that. So phi1 is just basically the node feature information for node B. But also we have a sign-code classifier, which where we add this summary of the neighborhood. And they both are trained to predict the node label. Okay. Okay, so how this works? So to classify, first we have a training set. We build like a model here, it could be anything. And we build this classifier. So the goal here would be like to predict again the node label given these node features. And a second classifier, which takes advantage of the neighborhood, and to predict here the node label. But this one is called iterative. Why? Because in this one we're now taking the previous one, the relational, it was taking node features independent of each other. So we were just going through the graph by iterating the neighborhood overlap. But here we're building like a classifier that basically takes advantage of the neighborhood. So we have this summary statistic that basically says like how likely is gonna this node is gonna belong to this neighborhood. And we're taking advantage also of node features. And then, again, this can be applied to web page classification. Here, there's also an example. You can go through that guy. So I just skip this and we go to the last one. So far too good. Let me know also if I'm going too fast. All right. So loopy belief propagation. This is an algorithm that I think has some beauty. And I think the message passing, the framework, it was inspired by this algorithm. So basically, the goal of this algorithm is like we want to pass messages. So instead of looking at the neighborhood and by building a classifier or try to wrap that neighborhood into a classifier or having like something flat where we have the overlap like in the relational and iterative. This one is just, it has it's basically this. So iterative process in which neighborhoods nodes talk to each other. So we want to pass messages from a node to a node. So this is a bit like it has like a recursion because when we have to go through the whole graph. So at the end, it's just basically like counting the number of nodes in a graph. Where when we are in node 1, we continue passing messages like from node 1 to node 2 to node 3. And as you can see, that has problem when you have a cycle because you're going to go back. So that mostly like in terms of convergence. So this works like this. So it's called belief propagation because I want to update always like a belief. And how to update that belief? By propagating messages. So when I am node 1, I'm going to send information to node 2, and I'm going to continue sending messages to the whole neighborhood. So I'm propagating messages, and I'm saying this is the belief that my current update. So then we can build based on that, like just not embeddings. So in this tree, I think it's interesting. So going from here to node, going from node 7 or 6 to node 1 basically will be like 7. Why? Because we're going from node 1, 2, so we have here, until here like 3 messages. If we get until here, we have this node is going to propagate information, and this node is going to propagate information, but also of the children. So up to here we have 5, and to get here we were going to continue propagating information. So from here to here we have again 1 message, and from here we have 5 messages, and this loop, so we have 7. Okay, so that's so that's basically how the algorithm works, but how this is learned. So for this algorithm now,
I'm sorry.
Yes,
so I had a kind of a question about this. So I see how we can propagate the messages in a line graph or in a tree, but in an undirected graph, like the example that they have here, the I, J, K, UV example, how do we choose which edges end up becoming the incoming edges, like incoming edges for the message, and which edges becomes the outgoing edge?
I think this one works only in directed graphs. I'm not sure it works in undirected graphs.
Oh, okay.
Yeah, because I think in that case you have again cycles.
Yeah, yeah.
Yeah.
Unless it's a tree.
Yeah. But it is a good question. I'll just write it. Like if I find something, I'll let you know in the chat.
Mhm.
1 second.
Well, the original loopy belief propagation method comes from probabilistic inference. And as far as I remember, in there you introduce a special node type called factors, and then you pass messages from nodes to factors and then from factors to nodes back. And I think this should fix most of the issues.
Yeah, actually, this one is like belief propagation is the original algorithm. And loopy belief propagation is the one that introduces like a probability, and then you have a factor model. So this is like a probabilistic graphical model where you want to send, like, you assume that every node is a probability, and you just send messages to each one of the factors. So this is directed. And then the generalization of that is called expectation propagation. So this is again a message passing, but now you assume probabilities in each of the nodes. But now in a probabilistic model, this becomes super hard, like to infer and to train these models. That's what I think, like those methods are not that popular. But now sending information from node to node, you have like a Bayesian error network. In each node, you have like a probability of how likely this node is to belong in this neighborhood. But instead of sending, like here, you're sending like just a value, just one scalar. The message is a number. In algorithms like expectation propagation, you're sending like a distribution. So information of, you're sending an expectation. So how much this node is sending information, which carries information about probability. And then you build like a factor model and etc. There's some work that they try to make these models stochastic, but it's still like super hard to learn. I've seen like some works like with variational inference, and actually expectation propagation is just a technique, because you can apply it to anything, but you can apply like to a loopy belief propagation. It's actually so like as a generalization. But I think this algorithm is super nice, and yeah, I've been thinking even like how to apply this to GNNs, because I think this is even a generalization of a GCN. So if we're gonna see next lecture, a GNN basically is this formula.
Yeah.
So yeah, I think this algorithm is super nice, and this one is super easy also to implement.
So on this formula too, like the one they have at the bottom of the slide, where the message from I to J, so they sum over all states, and I didn't understand what all states those are, because it's summing over yi, and yi should be just one, right? Because it's like the class for I.
Yeah, just one number.
Oh, but there's a sigma over there.
Like, yeah. Okay. So this is the potential is a matrix. So it could be like, here is basically the probability of not I connecting with not J. So those two are connected. And then I want to add like a prior belief of how likely is this not to belong to this class. So, okay, let me see how to. Okay, the potential is just the matrix that says if these two nodes are connected, how likely is that they both belong to the same class. So this is a matrix of probabilities. Then the prior is a belief of this node belonging to this class. And this part is just the message that this passed through that neighborhood for that node. So I want also to carry all the information that node has for that class. Did that answer your question?
Yeah, I guess. So when we sum over all state, like the sigma in the pink box, we are basically summing over all possible classes that I can be, right?
Yeah, because this becomes iterative, right?
Yeah, okay.
And it's the same like with the GCN. That's what I say, like this algorithm is beautiful.
Yeah.
Okay. And also, yeah, what Peter was saying, like when you define like this in a probabilistic graphical model, this becomes now probabilities. And actually here is actually probabilities. But in a graphical model, it's because you design like how the model is gonna look like. And it doesn't even have to be like a probabilistic graphical model, because you can add here just like a factors. So basically that would be like what is a factor model. Then you can send messages. So that's usually solved with loopy belief propagation. But I think, yeah, this argument is super nice. I really like this one. So do you guys have any question here? How loopy belief propagation works? Yeah, I'll take that as well. So I think that's it. Then they cover a little bit about cycles, which is more like is a little bit tricky. By the way, I saw a paper that they cover like there's a difference between loopy belief propagation and GCNs. Basically, they show also that applying this with GCNs, it improves. But the only difference is that the GCNs can manage cycles. So I think we can finish at least this one. So that's it. So this lecture was mostly about knot classification. What is the problem? The main intuition that similar nodes are typically close together. So that's why we want to take advantage of homophily and influence. How do we solve this with a relational classifier, iterative classification, and loopy belief propagation? So questions there? I hope I was clear. I'm trying to go fast because it's already 12:30. Okay, so I take that as a yes. So next one is graph neural networks, finally. So here the main intuition is like, now we want to have like a function where we pass a graph and we learn like some embedding that where this embedding captures similarity. So this similarity is again like we can learn like some similarity of, in the case of like homophily, how close are embedded. So nodes that are embedded, they are close to each other. So that's the similarity that we want to capture. So we saw before, like in the decoder model. So the encoder basically is gonna give us an embedding, and in the decoder we're gonna get the similarity of two nodes having been similar or not. So that was our encoder-decoder model. And at the beginning, we defined like a shallow encoder, where we have a lookup, like a vector of a vector of size of the vertices, and we have a 1 when the node is there. So we just do a lookup in this big matrix, which is gonna be the number of nodes in the graph, and we just do a lookup, and that would be basically our encoding. But that one has a lot of limitations. One that is like is gonna grow exponentially based on the number of nodes, and also it's transductive. So we want to take advantage of inductive tasks, so we can apply to different graphs, and we cannot add like knot features. Okay, so what we want to take advantage is of the also like layering. So we can assume like in deep learning, we can have like, we can learn different graphs, or we can go to different tasks. We can learn like different we can learn different things in each layer. And also we can apply this to different tasks like knot classification, link prediction, community detection, and network similarity. So in the current toolbox that we usually have, machine learning has been applied for images where we have a grid, but this grid has a sequence. So even text has a sequence. Speech has the same sequence. But what happens with graphs is that this sequence is lost because there is no order. So here we have to take advantage of permutation invariant. So this topology that we always find in images, text, or speech is not the same in networks. But that's the beauty also, because a graph can be anything basically. So that's why the problem is hard. So we want to apply now, here will be like how to apply deep learning on graphs. So I'll skip these basics of deep learning. Basically just optimization, a loss function, a stochastic gradient descent, the forward pass and a backward pass, and how to do mini batches. And why we need non-linearities and so on. So I'll just skip that, but if anybody has a question, just let me know. So now we want to do deep learning on graphs. So as we saw before, we want to take advantage of the local network neighborhood. So we're gonna see how we have like an aggregation strategy and how we define the computation graph, so we can apply stochastic gradient descent and the normal toolbox from deep learning. And how can we stack like different layers? So we can take advantage of, as in CNN, where you can learn different patterns. So here, the setup is going to be the same. We have a set of vertices. We have the Gensis metrics to describe a graph. And we have a matrix of node features. And the goal is to either like just learn some embeddings, do classification, and do regression, and do clustering there. And these node features, it can be anything. So, okay. So the easiest way how we can do this just deep learning is just having just flatten all the vertices and put that as an input layer in an MLP. And we can go as deeper as we want and then make our classification. But what happens with this is that this is gonna grow as the number of nodes grows. So if we have graphs of different sizes, this is not gonna be applicable anymore. And this is gonna be also sensitive to the ordering. So it is a little bit tricky, like for the input, we have to have like a hash function or something that where we keep track of the order of the nodes. And especially in graphs, like most architectures, they are permutation invariant. So I think that's one of the properties of a GCN. And it's not the same like as in convolutional networks where you have like you can apply different filters and you can learn, but the sequence is the same. So we want to generalize the same, but in graphs. So it will be like just looking as a part of a graph, taking that neighborhood and slide that window. But again, a graph is permutation invariant. So how do we do this? So in that sense, we have a graph convolutional network. That was this paper. That basically it shows how to propagate information across like different features in a graph. And in this paper also they show like some connection with the Laplacian, and also they prove they have a mathematical part of how to why this framework works. So the main goal, it will be like how to aggregate a neighborhood first. So first, like we have this graph. So how are we gonna define the different layers? So for this graph, this is gonna have only one layer, but at the same time, this graph has like 3 neighbors. So B, C, and D. So B, C, and D, it will be. So here's gonna be for us for now, just like a black box, but somehow we want to aggregate the messages that come from these neighborhoods. But at the same time, this node has like 2 neighbors. So in this case, B has A and C. So at the same time, we want to aggregate this one. So this becomes like a process which is iterative. So the neighbors of the neighbors, we capture the local neighborhood, but as we have like different layers, we stack layers, we can have like different hops. So on these black boxes, basically what we want to add, like we saw before, this will be like the same framework as for loopy belief propagation. But now we want to add, like instead of having this transition, having these potentials, we want to have like a neural network. So in that sense, it will be like each one of the nodes is gonna define like the computational graph. So we want to learn this structure, and also we want to add layers. So and also like in GNNs, as we add layers, we say like more information from the embeddings gets information from nodes that are key hubs away. So if I have like 5 layers, I'm jumping until like 5 neighbors. So that's my neighborhood, the surroundings of that node that I'm gonna look. So now let's open this box and let's see how these aggregations are done. Okay, so the basic part will be just average all the messages and apply a neural network. So it will be just this. Okay, so it will be like, we have first like the information for the current node. And here we just average all the node embeddings for that neighbor. So like in this case, like the first layer, this, I have like 3 neighbors, B, C, and D. These are embeddings, so we can think of it as a vector of size D, and this is a vector of size D. These 3 are average, so here we just this part, and this one is just like another embedding. So this is gonna become just a number, and I have an update for the next layer of the node embedding. So in this case, I have an update of this node embedding that includes information of these node embeddings. So that will be the message passing, and also the information of the embedding itself. And we continue this as we add layers, and we're gonna end up like in the end, in the last layer with an embedding, with a node embedding. So far so clear. Yeah. So here, the good part also is like we have like these weight parameters where like we know we can apply this to different inductive tasks. And we can put this as a matrix formulation. So how does it work? The diagonal matrix, so it will be just a degree node. And we multiply this by the agency matrix and the node features or the embeddings. And this will be like just in a matrix notation. So I'll do that. Okay, so I think that's it, at least for GNS. So so this will be like the update function, the update equation, where it will be the same. So here we carry information of the message passing, and here we have the information of the current nodes itself. So far this part is clear for everyone. Well, we can go a little bit more. Okay, so now how to train this model basically is we can apply like the same techniques. Many of the techniques that we saw in lecture 3 for unsupervised tasks. The same loss function that it was used for random walls or the other tasks, or for supervised training also. We, like in this case, we can assume we want to predict it is not is safe or is toxic. So we can apply a binary cross entropy in this case, where we learn this node embedding and we have the labels. So we want to predict if yes, this is positive or negative, basically. And we're gonna take advantage under the classification weights. So this will be like just an MLP at the end to do binary classification. So we can think of now like we can stack different layers, and at the end just add a layer to do the task that we want. And the good thing, as I said, like here is this. Okay, so let's go through this one. So now like the GNN, we have like a neighborhood aggregation. We saw that that's important, how we want to aggregate information from incoming nodes. The loss function that we need for the embeddings. So that's gonna help us like to define like a similarity. We want to do batching because we want to execute in large data sets. And also we want to do stochastic gradient descent. we want to generate embeddings, and also we want to apply this to graphs that they were not part of the training set. So this all is done. We can now have like an inductive capability. We can generalize to unseen nodes. Basically, we're learning parameters that are shared to different graphs. So this can be applied to new graphs, and we can generalize hopefully to new graphs. So that would be it, like just the framework and how the GCN works. Is that clear? Yeah. So now GraphSage. I think this is a paper that was published in 2018 or 18 or 17. And basically they generalize the averaging function. They generalize this averaging function, and they propose a sampling method too. So basically we saw that in many, like in the GCN, one of the important aspects is how do we average these nodes to make an update of the node embedding. But in this function, it can be anything. So they define this aggregating function where they say this function can be anything as long as it carries like some permutation invariant. So we take account of the node order. So we don't take account of the node order. So it will be this. So the basic GCN basically would be this, where we just normalize the node information with it was done with the degree matrix. But they also like propose two other ways of doing it, like a pooling and then LSTM, where the pooling, instead of just doing average, they say, okay, let's just pass an MLP, and here order doesn't matter anymore, but they take advantage of the mean just to ignore like the order. So then it becomes this permutation invariant. And also an LSTM. That. And they also propose a sampling method of how to select nodes, but I think that's not in the slides. And I think that's it. So far, so good. Is that clear? If anyone wants to add something, feel free to. Okay, I take that as a yes. Okay, so we cover node classification, how to do message passing, the basic framework of GCN, and GraphSage. And GraphSage is one of the popular papers. And there's still a lot of research, just to touch a little bit there, like how to improve the message passing function. I've seen a lot of papers like PNAS, and they define, like they say, like the aggregator functions, you need to have like as many aggregator functions as the number of sets that you have. So, or you can and they basically combine different aggregator functions with the moments. So you can go up to moment n. So that will be your aggregation functions. And we can continue reading papers, I think, because there are a lot of papers that they just try to improve the aggregating function. So, okay. So I think we have 10 more minutes. So I'll try to go. I selected this paper for this week. So we start also touching with some papers, but I'll encourage you guys, so you suggest papers so we can all read, so we can make this more of a discussion. So, okay, so I selected line. So this paper is more in the line of node embeddings. We saw deep walk and not to back. So basically deep walk was an application of a word to vect to graphs, where they consider like random walks as words, like as a document, and they basically apply word to vect. And the improvement of this in not to vect, it was like in AutoVec that they propose a generalization where they say we want to control these random walks with two parameters called P and Q, where P it controls the local neighborhood and Q controls the global neighborhood. So one, it will be like deep first search, and the other one it will do what is the other one? Forgot. Okay, I don't remember, but one is local and the other one is global. So in this paper, they try to also touch that space, but also like how to scale this to large graphs. So they propose like we saw like the first order and second order of a graph, and basically they touch in that paper. So the introduction basically is gonna be a little bit why we need this. The related work is gonna be mostly metric factorization, deep walk, and this paper was proposed before not to vect. Okay. So here, okay. So this paper is mostly based on first order proximity. So first order proximity is only the how similar is a graph to how similar is a node to other nodes. So we want the how similar is node U and node V. It just considers two nodes. And they also like propose the method based on second order proximity, but this second order proximity is mostly the neighborhood. So neighborhood 1 to neighborhood 2, how close are they basically? And basically for the model is mostly deep to walk. They try to model this first order proximity and second order proximity. So the first order proximity, they basically say, okay, let's build a probability matrix where we know like when we have an undirected edge, we're just gonna have this probability matrix where U is just a vector, an embedded. And the objective function basically is to get the proximity, which it will be just the distance. So in this, it will be here. So we want to get the proximity between a target proximity and the true proximity. So here I'm learning like the true proximity, and I want to compare this with a target proximity. And they apply the same objective function as in deep walk, and they replace these probabilities with carried divergence. So far so good. Okay. And for the second order proximity, now we need like a distribution for each one of the, like we need a distribution of how likely a node is going to belong to the other nodes. So then here we have like the probability of node Bj belonging to Bi. And this they model this basically with this function. She looks like a softmax. And again, you need like to apply the goal will be the same. Just having a K-like divergence where you have a context and you have the target. So you have this context and you have a target. And so over here. And this one, they have also lambda just to control how much we should pay attention to this. Similar like is in page rank, we have beta. And we apply the same KL divergence. Now basically is the model. So here the important part is like, instead of doing just a normal deep walk, sorry, the random walks, they try to model two things. One would be like the first order proximity that basically just captures the local neighborhood, and the second order proximity that captures a more global neighborhood. similar like what not to vec tried to do with P and Q. Okay. And also the other part is like the model optimization. Here they first do the same model optimization as in deep to walk. Just cross entropy with negative log likelihood. But they also propose an edge sampling. So they say, okay, we want also to scale this to go in large, execute this in large graphs. So they propose a way of sampling this. And basically that would be it, most of the paper. You guys have any questions? Okay. So they execute this and like different data sets that are actually quite large, 1 million of nodes, and some of them 500, 700. And as most of them, they obtain like good results. I'll touch you just here, the results. But here, I think most important than looking at the results is these papers, like how they try to capture node embeddings and like how they do like unsupervised learning. So basically, the main assumption came from deep work, and trying to model, or at least trying to learn these characteristics of the graph to do unsupervised learning. Basically, here they say, okay, the line with the first and second approximation. So basically, learning the local and global neighborhood, it actually helps like to, and in general, most of them, the first and second. So local and global neighborhood is what we want to see. So that would be it, like just for the paper. You guys have any question there? No. Yeah. So the last two things that we wanted to cover is the notebooks from the course. We were thinking and going through Collab 0 and Collab 1. I don't know, do you guys work on it, or how do you want to do? Also, like somebody sent the homework in the Discord channel. I don't know if you guys want to go through the homeworks, or do you want, how much time do you guys want to invest? I think we come to that into a discussion. Who wants to do the homeworks and share? I did the Collab 0 basically is super like self-explanatory. It's just like to get statistics of a graph, how to manage network X, and a small introduction to Python geometric. Parallel, you wanted to
So
say
I was thinking like the first homework is due around lecture 8 in the scheme, in the plan of the course on the website. So maybe we could discuss the first homework next time.
Okay.
And,
Another thing,
we
what
can,
is
like,
homework 1?
I'm sorry, go ahead.
What is homework 1? Somebody sent the link, but that homework 1 is from a previous course, I think.
Oh, yeah, I was about to send the link. Oh, really?
Yeah. I think I'll just open.
Yeah, the shared link was from course run in 2019.
Yeah, because they changed the format, I think, last
Yeah.
winter, I think.
Oh, so when do you think we'll be ready for the first homework then? There's also homework 0 in that.
Can you repeat, sorry? Yeah, so this one is from 2018 because it says like a year ago. Actually, So we could try to find the homeworks. If we find like you guys still want to do it, so we can cover that next week when it's gonna be due. And then we can also start with homework due. So we are aligned. So I think that we can decide now. Because we have only 2 minutes. And also the format, I'll be like super grateful if somebody wants to volunteer just to cover the lectures, or if you guys have any questions, just let me know. So it's a lot to prepare, like both lectures and paper, everything.
Yeah, so I was thinking for future meetings, we could probably assign roles. One person can take one lecture, the person takes one more lecture, and somebody takes a paper, and then somebody takes a collab or a homework. So we'll need like 4 people.
Yeah, if somebody wants to volunteer, that would be great. I always write in the chat like at the end. And it could be even less because the lectures are super well designed, I think. And we can take just one section. So it will be like 20 slides. So you guys have time like at least to have like a very discussion. And if you don't understand like something, just let me know. I'll try to do my best. And same, like either if you guys want to cover the whole lecture or just a section, that would be perfect. And for the paper too. Like next week, I suggest papers for papers. I still love PPR and Go, but we can start covering papers of graph neural networks or something like that. So the foundational papers most, I think. Is up to you guys, but I suggest some papers, but so just make sure also to vote with paper you guys want to cover, or if you have like any suggestions, just let me know.
So next time I could try to go over the Go paper.
Okay, so you present the paper. Does anybody wants to take one of the lectures? Next week it will be just we continue with GNNs and applications of GNNs. Does anyone wants to try? In the meantime, if somebody decides, for collab 1 also, I'll take a little bit longer. This one also shows the basics of graphs. I did this before. It's super easy to do it. Like I did it before the meeting. So one is just computing how to do the average degree and compute different coefficients with network X, and implement the main equation for page rank. I think this is a good exercise too. So try to do it. So I did it here. I'll share the notebook also with the solution you guys want. Centrality, same. It's just writing the question. And then there is with Python geometric, train like a process a data set. I think this is important. Get like negative edges. Get embeddings, how to build embeddings, and then train. So that will be the part of the training here. And write the accuracy function. So then train and then plot. So that would be it. I think we don't have time to go through every step, but I can share the notebook too if you guys have any questions. That would be it. Like, do we have like, does anybody want to volunteer next week for the second part of GNNs? If you want to volunteer only for one specific section, it would be also great. Or applications. Nobody? Sama, Beishak, Risky, Aris. I think we have some new people. Maybe we should go do like a round of introductions next time. So we make this more dynamic and it's not only me talking. So, okay, for next week, Parul, you present like prepare and go.
Yep.
Let's see if somebody wants to do the slides, or we'll see how it goes. And also for the homework, if we find the homework for next week, homework 1, we could try to work that for next week.
Or we could start with homework 0. That looks
Oh, was it like homework 0?
there is the homework.
Oh, yeah,
0.
you're right. You're right. Oh no, wait.
I mean, it's not on the schedule because I think this is a new one, but on the GitHub repository of that,
Oh, you mean this one, right?
there is a homework 0.
So you want to try like homework of the previous course, because this one is 2019.
Yeah, but we don't have the homework. Do we have the homework for the new course?
No, but I was saying like if we find that one, we can also start with homework 1. Okay, so in the meantime, let's chat and let's
Yeah.
start with this one, and we'll discuss next week if anybody had like a problem. But I'm saying now because mostly like I remember like CS 224W, the course from 2019, it used to cover a lot of the traditional ML in graphs. So I'm supposing this is a lot like how to get a statistics model. And I think a lot of this part we didn't cover. So okay, let's start with homework 0 and see how it goes. So anybody wants to add something else? No. Okay, so I think that would be it.
Okay,
Peter,
so
also, yeah, sorry. Also, don't forget to add the group to the calendar.
yeah, I just received the invitation, so I will do it. Okay, so if there are no other questions, I think this is it for today. So thank you, Javier, for going through the slides and presenting all the other stuff. And well, see you next week then.
Yeah, thank you so much, guys, for joining. And as always, let me know if any questions, suggestions, we want to improve, we want to make more dynamic this. So feel free to leave any suggestion, please. And if we have volunteers for next week for any of the sections, just type it in the chat. All right. Thank you so much. See you next week, guys.